Hello again. In today's lecture, we're going to be focusing on how we move from the DFT to the FFT. So we observed in the last lecture that in order to speed up the DFT, we basically use the symmetry property of it. Basically that we only need to calculate for half of the total factors here, and then the remaining half is just going to be the negative of the original half. So W naught of 8 was negative W4 of 8, W1 of 8 here is going to be negative of W5 of 8, and so forth. And then we also took advantage of the periodicity property, meaning that if the total factors exceeded the initial index, if we went here to W8 of 8, it's just going to be the same as W0 of 8 in order to actually speed up our calculations for the DFT. Now if n is actually a power of 2, we can even speed up the DFT more, and we can split the DFT here into two series where we only have odd indexing sequences separated by itself and the even index sequences being separated by itself as well. So as such, if we had a 16 points here that we need to do the DFT on, and we took the indexes here accordingly for each one of these 16 points, we can separate this accordingly into two signals of 8 points. Where the even index sequence here is grouped by itself, and the odd index sequence is also grouped by itself here accordingly. So as of such, if we try to mathematically represent this using the DFT equation, the DFT equation here splits accordingly here into even terms and odd terms. And the even terms here are represented by 2r, and the odd terms here are represented by 2r plus 1, where r basically gives us our index. We can continue along these lines, keep on splitting at each one of these levels. So we can move from one signal of 16 points here to two signals of 8 points, then 4 signals of 4 points, 8 signals of 2 points, and 16 signals of 1 point. And to give you an idea how we actually do this from moving from this first level here to the second level here, let's observe this first even sequence here. And let's say in this case we actually plot indexes for this even sequence. So this will be 0, 1, 2, 3, 4, 5, 6, 7. When moving from the first split here accordingly, we also took all the even indexes here for this sequence and grouped them here accordingly, and on odd indexes here for this sequence and group them here accordingly. In this case, because we're only focusing on this sequence here, being the even sequence, if we split this accordingly and we go back to the indexes, if we take only the even indexes for this sequence, that'll be we will take 0, 4, 8, and 12, and we can separate that here accordingly. And if we take the odd indexes, this is going to be 2, 6, 10, and 40. And we separate it here accordingly. Similarly, we can also do this for the odd index sequence, where the even indexes here are going to be 1, 5, the odd indexes here is going to be 1, 5, 9, and 13. And the even indexes here is going to be 3, 7, 11, and 15. And we can keep on repeating this process, keeping going on all the way down until we get individual points here accordingly. So instead of doing a full 16-point DFT, each split represents how we can keep on speeding up the DFT by having less points to calculate for. So this here actually is if we perform only on this sequence here. This is a 16-point DFT, but because we split it here accordingly, now we have two 8-point DFTs, and this will be 4 4-point DFTs, 8 2-point DFTs, and then a 16 1-point DFTs. These splits that we observe here and speeding up the DFT is actually how we move towards the Fast Fourier Transform of the DFT, also referred to as the FFT. So basically, it's a very computational effective way of calculating the DFT and splitting it up accordingly into less points to calculate the DFT for. And as of such, this also helps us with parallel processing, because now we only have less points to calculate the DFT for, and we can then split up the DFT calculations accordingly into each one individual cores if we have multiple cores in any sort of processor. So the first split in the DFT equation resulted in the following equation that we saw in a few slides before. And the more identical terms you tend to have inside here, it means you're going to have to lower the number of new items to compute, so it actually speeds up the calculation quite a lot in this particular term. And this is because that total factor value here that you observed for the odds sequence, which will be Wn of k 2r plus 1, can actually be split up here accordingly, because this is an add addition in the index here, to wk of n 2 of r multiplied by wk of n. And as such, when you split this, the total factors here, being wn squared here and wn squared here, now become the same. And then we can take advantage of the symmetric property of the total factors. There's one error on the slide. Remember that this here is going to be the negative reflection of this. So therefore, we can split this up even faster into this form of the equation. And all these splits that we observe here in order to speed up the DFT is just showing you how you can move from the DFT to the FFT. So observing each one of these equations here, or each summation series, this actually is just two 8-point DFTs from moving from the 16 points, or basically n divided by 2-point DFTs. So let's actually start observing what are the time savings with respect to this. Originally, if we extract out how many calculations we need to do, the first part was going to be n1 divided by 2 squared multiplications. The total factors is going to be basically a next n divided by 2 multiplications, and then the next summation point here is going to be n divided by 2 all squared as well. And if we watch the calculations here, an 8-point DFT, sorry, an 8-point FFT means you're going to have only 36 multiplications. Whereas if you did for the DFT, there's going to be 64 multiplications. So you got a nice, good enough saving. For the 1024-point FFT, that means you need to calculate for this amount of multiplications here. But this huge number here, which was in the millions, that was for the DFT. So you get a lot of time savings here accordingly by reducing the amount of calculations you actually need to perform. So the percentage increase, or to say the percentage decrease in how much time you actually need, is roughly about half. And that's a good speed up. It's when you actually observe how you speed up the DFT to the FFT. So in splitting the DFT, where we actually observe how we move from one 16-point to two 8-points, those actually, the term for that is referred to as a decimation in time, or also when you observe it in frequency, it's referred to as decimation in frequency. But because we are observing this with respect to time, it's just a decimation in time. And in particular, you keep on decimating the signal until you only have a series of 2-point DFTs to perform the FFT. Now, this method is referred to as a radix 2 FFT. And this only works when the input sequence is actually a power of 2. Let's say, for instance, the index sequence was not a power of 2. What you'll need to do in this case is that you need to zero pad up to the next available power of 2. So, for instance, let's say you had only 5 points in the x of n. You will have to zero pad the end of the signal until you get up to 8 points, and then you actually can perform the FFT accordingly using this method. So let's actually observe how we actually would start doing an FFT for a 4-point input. So if we decimate this 4 points here, and we split it into its even sequence and odd sequence, the equation becomes this form here. And actually, let's start expanding this and observing any patterns. So when we actually expand this out, and we start substituting values for k equals 0, then 1, 2, and 3 accordingly, we want to observe what happens when we do it for x of 4 naught first, and keep on going. So when k is equal to 0, that means we're going to have to solve here initially for x of naught and x of 2. So let's actually put these on the left hand side representing the inputs. X of naught and x of 2 here needs to add together, but x of 2 here needs to be multiplied by the first total factor, 0, naught, or 4. So we actually can draw this here accordingly to represent this calculation, because x of 2 here is multiplied by 0, naught, or 4, and the addition is going to be to x of naught. Similarly, with x of 1 and x of 1, 3 here, we can represent these here accordingly, and we can actually do the same calculation here, because x of 3 is multiplied by 0, naught, or 4, and it adds to x of 1. The final result is just basically a summation of these two, but we also have to cater for this w naught of 4 here accordingly. So we make sure that we cater for it here by putting this block here in order to obtain our x of 4 of 0 being our output. Now this is only for when k is equal 0, so this is actually just only a quarter of the full diagram. So let's observe it for k equal 1. We do the same thing as before. We use x of 0 and x of 2 here when we represent the inputs, and similarly x of 1 and x of 3 here is going to be represented as our inputs. W2 of 4 here is common. So x of 2 here multiplies by W2 of 4, x of 3 here is multiplied by W2 of 4. The last factor is this addition here and this W1 of 4. So in order to obtain x of 4 of 1. At this point you actually might be seeing some sort of similarity pattern. So actually you observe it for k equals 2 and see if you actually can formulate it yourself. In particular, you have W4 of 4 here, but remember the periodicity property of the total factors means once the index starts repeating, this is just equal to W0 of 4. It's basically the same value. And W4 of 4 here repeats. Note that how we mapped it, we had x of 0, x of 2 here, and then x of 1, x of 3 here. These two here values here are still being multiplied by W0 of 4 here accordingly. And then the last part here for the addition and this W2 of 4 multiplication, it maps accordingly to the next input. And answering why I said why this is W0 of 4, this is the periodicity property of the total factor value. And similarly, if we do it for k equal 3, we can do the same mapping all the way down to get to x of 4 of 3. If we map all of these quarters here and show all those visual mappings that you just observe and overlay each one of these, we basically see that there's some sort of pattern as we keep on going. And this pattern actually is referred to as a butterfly pattern. The reason for this being is that the center here represents the body of the butterfly, and each triangle here represents the wings of the butterfly. So for this part here, this center here represents the first wing here and the second wing here accordingly. So our butterfly calculation for each one of these quarters is actually represented by this being here the first butterfly and then the second butterfly. And we're going to observe in the next lecture how actually we take advantage of the butterfly calculations in order to actually perform the radix 2 FFT. So the butterfly calculation here, if we actually map it out and we calculate for each one of these total factors, we actually get our calculations here accordingly with respect to these using the graphical indication or the visual indication for actually calculating the FFT. So, even though we're doing the radix 2 FFT algorithm, there are many other efficient algorithms for performing the Fourier transform or the DFT. But for this course, we're going to be actually observing how to do the radix 2 FFT and actually how to actually perform the calculations by hand. So it's important in the next lecture to actually pay attention how we actually do the radix 2 FFT and actually how we do the calculations by hand accordingly. And in particular, we're going to be observing how we actually do the butterfly calculations in an actual example. The simplified butterfly actually can be implemented on a DSP very effectively, very efficiently, and they can perform other operations that the signal is required because how the DSP is programmable. And to give you an idea, 1024 point FFT can be actually done in under 5 milliseconds for any modern day DSP. So actually pretty quick. So I'm going to have to backtrack a little bit and show you guys how the speed up actually occurs accordingly. So if we did the DFT on this sequence here, and we actually need to calculate it for the output frequencies here, going from capital X0 to X of 7, we actually observe here that because we zero padded accordingly for the last 3 values, the DFT actually can reduce down to the required values. And the first thing we normally did if we were calculating for the DFT is that we will have to calculate for 12 factors. One thing you guys need to try in particular is that you need to, instead of having this 8-point DFT, this 8.12 factor, you might want to try calculating for a 16.12 factor and then see how it does it overlay, and you may see some similarities accordingly. So if you actually want to calculate the 12 factors here and you're using MATLAB, this actually is the MATLAB code for it. So this actually will generate all the 12 factor values for you in one shot. And this actually is quite effective for practice. Also, because of the periodicity property and symmetric properties of the 12 factors, you don't need to calculate all 8 values. You only need like the first 4. And then the remaining 4 is just going to be the negative of the first 4. And anything that keeps on exceeding the indexes is just going to be a simple rotation because of the periodicity property. So these values here actually been calculated for you guys, and what I'd like for you guys to do is actually to calculate for X0 to X7 as your homework. So I'll give you part of the answer so that we can verify it. X of 0 here is going to be 15. X of 1 here, because we're dealing with 12 factors, is actually going to resolve into a complex factor. And this is because the signal is no longer constant in nature. The signal is actually a ramp. So we're going to actually start observing that we're going to get complex values for frequency comments. So I want you guys to actually calculate for X0 to X8 and observe what's going to happen. And then we're actually, in the next lecture, we're actually going to do the FFT algorithm, or the radix 2 FFT, to observe that how we get the similar values. So, to ensure that you actually practice this before moving on to the next lecture, because then we're going to observe how the FFT can actually speed up the calculations here accordingly.